So today's notes are going to reinforce some of those concepts that you looked at in the PhET assignment yesterday as we talk about projectile concepts. But again, before we get to that, let's go ahead and go over the warm-up, which also would have been answered by what you looked at in your PhET yesterday. So question number 1 says air resistance makes a projectile travel, and then again, you're just kind of filling in the blank here, greater or less distance. What do you guys say? Shorter distance, yeah. So less according to this, but I think it is shorter in my open math. But yes, air resistance, if it is present, is going to both reduce the vertical and horizontal displacement of that projectile, or rather the maximum height and the range of that projectile. The second question says, how does the horizontal velocity of a projectile compare just after firing versus just before impact? This question is assuming that there is no air resistance. And this is something that you looked at in the PhET whenever you were looking at the velocity vectors, and you should have been talking about what happens to the horizontal ones versus what happened to the vertical ones. But here I'm just asking about the horizontal. So what did you guys notice about the horizontal velocity of your projectiles? Yeah, it stayed the same the whole time. Hopefully you saw that in the simulation. We're going to be talking about it again today. But go ahead and make sure that you have answered those questions for today in My Open Math. If you haven't yet, please make sure you do that so that you're getting that grade for your warm-up. So again, today we're going to talk about those same concepts you looked at yesterday, add a few more in. We're going to take some notes. So I would, again, strongly encourage you to have out a notebook so that you can jot some of those things down. And then you do have an assignment that you can start at the end of the period. Maybe you'll finish it, but if not, it will be homework 703.1 Projectile Concepts problem set. Will be our first problem set for this new unit. All right, so let's go ahead and get into the notes for today with this question. Okay, it says, a bullet is shot horizontally, and at the same moment, another bullet is dropped, another bullet at the same height is dropped. Which will hit the ground first? What is your reasoning? Okay, so again, the idea is you have a bullet fired straight ahead, and at the same moment that you fire it, you drop another one from the exact same height. Which one will hit the ground first? If you think the bullet that is fired from the gun will hit the ground first, raise your hand. Okay, what about the one that's dropped? If you think that one hits the ground first, anybody? There's a couple of brave people willing to raise their hand. What about the rest of you? What do you think?
I think it's the same time.
Same time? That is the third option. Okay. So this is actually a very famous thought experiment in physics, but they did it on the Mythbusters. I don't know if you guys have seen the Mythbusters at all or this particular episode, but I have the clip in here so you can see it in and actually carried out. So we're going to watch this clip, and then we'll talk about what's going on and why they got the results that they did. So they're saying it's effectively the exact same time. It wasn't perfect because no experiment is going to be, but they did show what some of you thought, that they would land at the same time. And this is another apparatus showing the same type of thing. This allows one of these balls to be dropped while the other one is fired forward at effectively the same time, and you notice the same thing that they hit simultaneously. Okay. And that is because whenever we talk about projectiles and projectile motion, projectiles are in free fall, just like the objects that we were dropping from rest or talking about dropping from rest last semester. Okay, so a projectile is an object upon which the only force acting is gravity. And we talked about that being true for every object in free fall as well. Thus, a projectile is in free fall, and the vertical acceleration of a projectile, even if it's thrown forward, it's still going to fall in the same way as something drops straight down, and that means it's going to have vertical acceleration due to Earth's gravitational field at a rate of negative 9.8 meters per second squared, or 9.8 meters per second. Okay, and so yes, they did hit at the same time. So if you thought that and you hadn't looked ahead, good job. If you didn't, that's okay. It is a common, like I said, misconception, if you will. A lot of times students want to say the one dropped straight down. Sometimes they want to pick the other one, but they do hit at the same time. Okay, so again, we're going to recall some stuff about free fall. Before we get into the stuff on projectile motion, let's just make sure we remember some things from last semester. We know, or hopefully we know, if not, write it down, that an object that is falling under the sole influence of gravity will have an acceleration of negative 9.8 meters per second squared because there are no other forces acting on it. No air resistance, no lift, no push or pull from anything else. And so if we have an object in free fall, we know its acceleration will be due to gravity. Okay, and so we can look at scenarios like this one. This guy's dropping a ball off of a building or the edge of a cliff or something. And just a few questions, and this slide is actually from your notes last semester, but it says, where does the ball have the least velocity? I've got 4 points labeled there, A, B, C, D. Which one of those would have the least velocity? A. Okay, we know it's going to start out moving slowly and that it's going to pick up speed as it falls. Okay, so it's going to have the least velocity at A, and then B, and then C, and then D. What about the second question? Where does the ball have the least acceleration? It's the same everywhere. That was the trick question I kept asking y'all over and over again last semester. But it's the same everywhere. At A, B, C, and D, the acceleration is still negative 9.8 meters per second squared at all of those positions. Okay, we didn't talk about this with free fall, but we have talked about momentum, so let's see if we remember that as well. It says, does the ball's momentum change as it falls from point A to D?
Yes.
Yes. Okay, remember that momentum is mass in motion. It's mass times velocity, and if your velocity is changing, obviously your momentum would be as well. Okay, so again, we said that we have the least velocity at point A, that the acceleration is equal everywhere, and that the momentum increases as the ball gets faster. We're going to be bringing back in a bunch of topics from last semester. So the same way that we were kind of bringing them back in every single unit, we're still going to be looking at them because we have to. We have more, they all rely on each other, but we also are going to be coming full circle back to momentum and energy in just a couple of units. So we need to make sure we keep that fresh in our minds as well. All right, so again, when an object is in free fall, the force of gravity is the only force acting on it. That means if we say it's in free fall, or if we call it a projectile, we are implying that there is no air resistance. That means that the only force is gravity, and that means we can assume that our acceleration is due to that gravitational force. Objects in free fall could be an object like a ball. It could be a ball that's dropped from rest. It could be a ball thrown up or down in the air. It could be something launched as a projectile. This was actually in our notes last semester. So projectiles, although we hadn't talked about them yet, were listed there too. But it could be thrown forward, okay, or up and at an angle. But it's considered to be in free fall the second that it leaves this person's hand. Okay, so as soon as it leaves the hand, now we're dealing with something in free fall. So the moment that it leaves his hand, the only force acting on it is gravity. Of course, when it's in his hand and he's pushing it up, still there's another force. Okay, so again, whenever we talk about free fall, we're going to be talking about that object the moment it leaves whatever apparatus or whatever person is throwing it or launching it. Okay, so we're looking at that second afterward, or that instant afterward, and we're looking at it through the instant just before it hits the ground. We're not looking at when it hits the ground. Obviously, it's not in free fall then. So when we do our calculations later on, you're just looking at the portion where it's in free fall. Okay, the vertical motion of this projectile that he throws forward is the same as the vertical motion of something that is being dropped straight down. That's what we talked about in the warm-up as well. But you can see here in this animation, he's throwing this ball and the trajectory is marked. This guy up here that's in a cloud or something is dropping one at the same time, and it's just showing you that they're going to hit the ground simultaneously because they have the same vertical motion. Okay, so we have different types of projectiles, things that are dropped, things that are thrown upward or downward, that they're launched vertically, things that are launched horizontally, like this cannon right here that's firing this cannonball horizontally off the edge of a cliff, or things that are launched at an angle, where you have something like this boy throwing the ball that's up and forward. All of those are going to be types of projectiles. Prior to this unit, we had talked about the first two types because we discussed them in our free fall unit. But now we're going to be talking about projectiles that also have horizontal motion. They're not just up and down, they're also maybe being thrown forward or up and forward or whatever else. And so all of these are projectiles, all of these are in free fall. So again, let's look at some numbers with this just to refresh our memories. But it says, for the sake of simplicity in this example, I have rounded gravitational acceleration to -10. This is just easier to work with, and it's pretty close to -9.8 anyway. Okay, and so if you look at this, we did tables like this in our free fall unit. But this is what it means to accelerate at a rate of -10 meters per second squared. It means that each second that this object is falling, its velocity is increasing by -10. So you go from 0 to -10 meters per second after 1 second, to -20 meters per second after 2 seconds, to -30 after 3, and so on and so forth. The vertical velocity of the projectile increases 10 meters per second each second as the object falls. This is also true if it's launched forward. Okay, so this one's just being dropped straight down, but if we look instead at this guy, those values are the same. The y velocity values look exactly the same. The difference is we would also have to include some horizontal velocity values. And so when we start looking at these projectiles that also have horizontal motion, we are going to have to analyze the horizontal and the vertical separately, the same way we did when we did forces last semester. Okay, and so you can make a table like this, which I would encourage you to maybe copy down so you have it as an example. But a projectile launched forward experiences vertical acceleration exactly the same way that the one dropped from rest did. Those numbers are the same, 0, -10, -20, -30, -40. But it also has constant horizontal motion. Okay, and so there's no forces acting horizontally, so there's nothing that would cause it to speed up or slow down. Remember, we don't have acceleration without that force. So that horizontal velocity will be constant. I just said 2.8 here based on where this thing landed. So 2.8 meters per second each second horizontally. But its vertical velocity is, of course, increasing while its horizontal velocity remains constant. That is what you're going to see with every single projectile that we look at that's launched forward. They're all going to have this same pattern where we have this acceleration in the y direction but constant velocity in the x direction. And so you have to keep them separate because you have two different types of motion, acceleration in one direction and constant velocity in the other. All right, what about this question? What happens to the kinetic energy of the ball during the 4 seconds of falling motion?
Gets greater.
Yeah, it gets greater. While the horizontal velocity is not changing, the vertical is. So the resultant, if we were to add them together, would be changing, and it would be getting faster and faster as it falls, which we already know because we can see that with our y velocity. Okay, but that, if you have an increase in that velocity, it means that you have an increase in kinetic energy. So if I have a change in my kinetic energy, does this mean that work is done on the ball?
Yeah.
I know I'm asking you all a bunch of questions from last semester, but yes, it does. Remember, work is equal to change in kinetic energy. So if I have a change in kinetic energy, I have work. What did work on my ball? Remember, work we get if we have a force that causes displacement. So what was doing work? What was the force? Gravity. Okay, so we have work done on the ball by gravity that causes the ball to gain kinetic energy as it falls. Again, I told you we're going to bring a bunch of stuff back into our discussions because we just want to make sure we keep that fresh, because we're going to have a whole unit where we come back to energy and momentum. All right, so here's just some vocabulary terms that you need to know. I've already said them a few times, but you might want to write them down. But trajectory and range, they're just two of the terms that you're going to see when we look at projectiles. But the trajectory of a projectile is just its path. And when we look at these projectiles, whether they're thrown forward or if they're launched at an angle, it's going to follow a parabolic path. You're going to get a curve shape to the trajectory. So its path will look like the image that you see there. The range of a projectile is the horizontal displacement. It's how far away the projectile lands from where it's launched. And so you can label the range. I've labeled it down here on my diagram. Delta x is the variable that we use for range. It's our change in our horizontal position. Delta x, change in x. And in this case, it's like 11.3 or something. But it is how far away it lands from where it was thrown in this case. So again, trajectory is the path, range is the horizontal displacement, or how far away that lands horizontally. Okay, when we talk about the trajectory, that curve that you see is created by the resultant of the horizontal and vertical velocity. So we have, let's say our horizontal velocity vector looks like this. And it's going to look like that the whole time because horizontally it's going to be the same length. It's the same each second. It's constant velocity. But as it falls, we get these vertical velocities. So we start out with no vertical velocity, and then it starts to increase, and then it increases more, and then it increases more, and I went off the screen. But you have this constant horizontal motion, but this increasing vertical motion, and that's what creates the curve. Okay, and so the resultant of the two, if you add them together, you're going to get diagonal lines that get steeper and steeper going downward in this particular example, and that's what you get, how you get this curved shape to the trajectory. All right, so these are some of the things you guys looked at yesterday in the PhET, but some different factors that affect the range, or maybe they don't affect the range. We're going to look at some that don't as well. But when we talked about, or when you looked at changing the initial velocity, hopefully you saw that the faster the velocity was of that projectile launched forward, the farther it goes. Okay, you got a longer range. Air resistance, that was another thing I had you guys test. But air resistance reduces range, and so if you want a longer range, you need less atmosphere. You need to do the same test in a vacuum chamber or something. Okay, but less or no air resistance is going to give you a greater range because air resistance reduces range. The initial height, if you launch it from a greater height, so if I launched a projectile from, my desk versus, from the top of the board up here. Okay, obviously the greater the initial launch height, the greater the range is going to be because it's in the air for more time, and that means it has more time to move forward, let's say 2 meters per second for each second that it's in the air. If it's higher, it's got more air time, and therefore it's going to get more range. Okay, some other factors, we did not test these, but I do want you to write them down. These were not in the PhET yesterday, but I want you to be aware of them. Okay, now the reason actually I think I could have changed both of these, but they're not things we can really test. Well, the first one anyway is not something we can test in this room, but gravitational field. Okay, if you have a smaller gravitational field, you will get greater range and height. Now, obviously, I can't test that because the gravitational field is what it is on Earth. But if you were to launch a projectile under otherwise identical conditions on the Earth and then do it on the moon, you're going to get greater range on the moon. Because on Earth, it's going to fall at negative 9.8 meters per second every second. And so you're going to have less air time than something where you have less gravity. On the moon, it's going to fall at a slower rate because the moon has about 1/6 the gravity of the Earth. Okay, so if you have less gravitational field, you're going to have greater range and height. Thus, a projectile's trajectory is different on different planets. If you launch it at an angle, now this is something you could have tested. Maybe you played with the PhET afterward, I don't know. But if you launched it at an angle instead of horizontal, you will also get greater range. And when we look at this later on, the, most ideal angle for your launch to get the greatest range is 45 degrees. It's the perfect mix of horizontal and vertical because it's halfway between the two. And that's going to give you the greatest range. If you play with the PhET and you want to look at it, you'll see that. But as you move away from 45, whether it's higher or lower, like 40 degrees, 50 degrees, those are both 5 degrees away from 45, they'll be the same as each other, but they will be give you less range than 45 degrees. Okay, so that's your maximum range is going to be at an angle of 45 degrees, and then as you move away from that angle, your range will get shorter. Mass was one thing I had you change, but hopefully you saw that it had no effect at all. And we talked about this in free fall as well. In fact, this is from one of the videos I showed you in the free fall unit where they dropped a bowling ball and a feather in a vacuum chamber. And they fall at exactly the same rate if you remove the air. And so the same thing is going to be true when we talk about projectiles, and we talk about projectiles in this ideal scenario where there's no air. Okay, then the mass is going to have no effect. Now, obviously, in the real world, there is some effect depending on how much air resistance affects that object. But for this class, for these ideal circumstances, we're going to say mass has no effect on the projectile because it doesn't if we're talking about something in free fall. If the only force is gravity, that means there is no air resistance, and that means that mass will not affect it. Everything will fall at the same rate. Does anybody have a question about any of these so far? We saw a lot of these yesterday. No? Okay. All right, for a projectile launched forward at an angle, the trajectory is parabolic. It looks something like this. This is a kickoff or something, or a punt. But if it's a horizontal launch, it'll look like half of that. Okay, if you instead launched your football out of a cannon off of a cliff or something. But you still have a parabolic trajectory, okay, whether it's launched up at an angle or whether it's launched just straight forward. You're going to get that same curve to it. Okay, so if we look at it, again, I told you have to analyze the motion separately. So let's talk about the vertical motion for a moment, and then we'll come back and talk about the horizontal motion. But vertically, we have free fall and acceleration downward at negative 9.8 meters per second squared. And so if we look at the vertical velocity vectors, they're going to get longer and longer and longer as it falls. Okay, because your y velocity gets faster due to that acceleration due to gravity. Looking at the horizontal motion, on the other hand, it's constant velocity. There are no horizontal forces. There's nothing that would cause my horizontal velocity to change, and so it's the same every second, and all of those vectors would be equal in length if I was looking at the horizontal velocity, because there are no horizontal forces. So we have constant x velocity as this object falls. And again, those two act together to give us the parabolic shape that we've been talking about. But the horizontal motion is independent of the vertical motion, and when we do the calculations, we do need to keep them separate. They work together to give you the shape, though. All right, so hopefully that kind of helped to recap some of the stuff you saw yesterday in the FET, and it should be enough to make you feel comfortable answering these questions. So please make your way to My Open Math and find the assignment 702.1, Projectile Concepts problem set. This is your first problem set of the unit, and it is due by 11:59 p.m. tonight. If you have questions as you are working on it, please don't hesitate to ask. You can work with each other, but of course, if your neighbor's not sure, make sure that you ask me before you leave the room today.